All right, so yes, now that we have accepted the continuum approximation and understood its role and how it relates to molecular theories, let's briefly take a look at the standard equations that we will be working with in the rest of this course that form the basis of the continuum mechanics of fluids. So these are equations that you would have seen before in your earlier courses, of course. So let's look at first, well, for an incompressible fluid, that's what we will really be looking at. Yes, this is essentially what we'll be doing. So the first we have the continuity equation, which is really expressing mass balance, or the conservation of mass. And for an incompressible fluid, this just takes the form of the divergence of the velocity is 0. Yes. Then we have the Navier-Stokes equations, which really is, well, it's really force is equal to mass times acceleration, but for a continuum material. And this in vectorial form looks like this. So du, the capital D here denotes the material derivative or the convective derivative or the Lagrangian derivative. It represents really the acceleration of the material. So that is balanced by pressure gradient. And then you have the viscous forces. Sorry, this should be V. V is the velocity. Yes, the viscous forces, and finally gravity. Yes, I'm missing a density here. Yes, that's about it. So this here is the viscosity, and this is the form of the stresses that we get for a simple viscous fluid or a Newtonian fluid. And these are the inertial terms, or the acceleration. This is the force due to pressure gradients, and this is the body force from gravity. So these two equations together, the continuity and the Navier-Stokes, are enough to describe the motion of an incompressible isothermal fluid where the viscosity and density are constant. Now in this course we'll be mostly dealing with these two equations under these circumstances, but as it is a course on transport phenomena, we will also be interested in understanding the simultaneous diffusion and convection of concentration of a species as well as temperature or energy. And so for that, let's also write down now the species conservation equation. Right, so if C is the concentration field, which denotes the let's say the mass per unit volume, or it could be the moles per unit volume of a species within the fluid. Then what we have is the following. Yes, so then what we have is the material derivative of the concentration with time. So the way the concentration evolves as you move along with the fluid in a fluid volume, material volume, is given by diffusion and the rate of generation. So this would be negative if there's consumption due to a reaction, for example. So here we have the species conservation equation, where you have convective effects sitting here. Yes, let me write down what this is, though I'm sure you would have seen it. So the material derivative, or the derivative as you move along with the fluid, is, let's say, for some quantity, yes, some scalar quantity b. The scalar quantity b could be one of the components of the velocity or the concentration or the temperature, for example. So it's the local Eulerian time derivative, which you will encounter again later as we go along, plus the velocity scalar product with the gradient of this quantity. Right, which in turn, if I expand it out, and this is the component form which we are familiar with. Plus Vz. Now here I've written it in Cartesian coordinates, but the same expression holds otherwise as well. Yes, anyway. Yeah, so that's our convective derivative. So this ddt of C incorporates both the local time dependence change in concentration at a fixed point, as well as how it varies due to convection. And here we have the diffusion term. This requires a constitutive equation, just as viscous forces require a constitutive equation. And indeed, you can see right here the similarity in these terms. And they are both this is why they're both described as diffusive effects sometimes, a diffusion of momentum. Although strictly speaking, viscous forces need not arise from such diffusion of molecules, except when it's an ideal gas. And in this case, indeed, the molecules can diffuse around by random motion and lead to this diffusive term. And in this case here, we have a rate of generation of concentration, which is due to a chemical reaction, let's say. Here, the form of this term is taken up by body forces and the pressure gradient, which in some sense generate momentum. Although such an analogy can only be made in limited situations, and that too in hindsight. And that's why in this course we will refrain or avoid talking about momentum conservation the way we do mass conservation and momentum fluxes and so on, but rather think of it as just a statement of Newton's law of mechanics, or Euler's law of momentum conservation, F equal to ma. Okay, so moving on from there, we then can look at the energy equation. Sorry. The energy equation in this case for a constant density incompressible fluid. So we are neglecting effects due to thermal expansion and as well as pressure compression, which will be valid and reasonably accurate for all the situations we're looking at in this course. Yes, so here again we have the convective derivative of the temperature capital T as we move along with the fluid. Actually, let me use theta for temperature, since we will be encountering, or rather we will reserve capital letters for tensors that we will encounter soon. Yes, so the substantial derivative of temperature is given by the diffusion of temperature, and you of course have a possible source of heat, which I can represent as S, which plays the same role as the reaction generating concentration. Here you have some source that supplies heat, that could generate heat. But then you also have, this is some external source of heat. But then you also have heat that's produced due to viscous dissipation. That is, the viscous stresses in the fluid themselves convert kinetic energy into, or for example, yes, the kinetic energy into thermal energy. This is the heat loss that is inevitable in pipes, in heat engines and so on, involving the flow of fluids. So this takes the form of V, where this is the velocity gradient tensor. So we will come back to this in more detail later on. Actually, I think it's better if I just write it in this form, because we will encounter this again later. Yes. So this is the correct form where this E is the symmetric part of the velocity gradient tensor. So remember that the gradient of a scalar is a vector, as we have in the case of the gradient of pressure here. But when we take the gradient of a vector, we in fact get a tensor. And we will understand this term in more detail shortly. Okay, so the point I want to make here now is that if you look at the, if you compare the species conservation and the energy equation, you see that they look very similar. You have this same role played by convection of the fluid. In this case, you have diffusion of concentration as well as diffusion of heat. Or here, alpha, known as the thermal diffusivity, in analogy with the species diffusivity, is nothing but the thermal conductivity by the density times the heat capacity at constant pressure. So alpha is the thermal diffusivity. This is the diffusion of heat. Here you have a source that could maybe come from the heating of an electric wire immersed in the fluid, radiation sources, and so on. So these are some sources that supply heat, or in fact can remove heat as well. And here you have another source of heat which is due to viscous dissipation. So if you have flow in a pipe, the viscous stresses themselves can produce, can cause a loss of work as heat. So that's the source of this term. But now if you neglect this term, let's say you say that this is approximately 0, as it would be for low flow rates of a low viscosity fluid. Then you see that the thermal equation and the species conservation equation look entirely identical. And this is the source of the analogy between heat and mass transport. At the same way, if you look at the equation for momentum, the Navier-Stokes equations, and here you say that, okay, I interpret gravity, or I combine gravity with the pressure gradient and interpret it as a source, then you have you again reach an equation which has the form convective and local time dependent effects being balanced by diffusion of either the velocity or concentration or temperature, and a source term. So you can see now that by looking at these equations that one could think of analogies between transport of momentum, concentration, and temperature. And really the source of this is in the equations themselves. And in the problems that we do during this course as we go along, you will see these similarities come time and again. What I want to emphasize here though is that this analogy or equivalence is under rather restricted conditions. For example, it only holds if the fluid is incompressible. If you start accounting for compressibility, a whole range of effects enters in both the momentum and the energy equations. Moreover, even if you take it to be incompressible, but you do account for the fact that the density could change with temperature, even though the density doesn't respond to pressure variations, you will still have an extra term in the energy equation that would break the analogy with the species conservation equation. And then even in the species conservation equation, this is the simple case where we have assumed diffusion to be given by a fixed law of diffusion, which is a constitutive equation, just like the Fourier law for heat conduction that's used in the energy equation, just like the Newton's law of viscosity for Newtonian fluid used in the Navier-Stokes equations. If any of these constitutive laws are violated and we have to use a different law, then again the analogy is broken down. So for example, even in the species conservation equation, if you have multi-component diffusion, that is diffusion of various species through each other and an ambient inert, then we can no longer use simple Fickian diffusion, and the equations take quite a different form. Okay, so with all these caveats, nevertheless, in this course we shall focus on circumstances which are quite wide and has many applications, where these equations do hold, and where we can think of especially the transport of concentration and temperature to be analogous, and we can represent both by speaking of the transport of a scalar, a single scalar. And that's what we will really be doing in this course. So you can think of this course as fluid mechanics combined with scalar transport. What will make things a bit interesting here is that we shan't simply look at cases where the concentration is merely advected along by the fluid as it diffuses, but one can also think of situations where the viscosity of the fluid, for example, depends on the temperature, as is very common in magma flows, as well as the flow of ice and other situations. So in such cases, the transport of the concentration or transport of the temperature by the fluid will affect the flow of the fluid itself. And that's a case that we shall also be considering both for concentration and temperature as we go along. Okay, so this was basically a brief overview of the equations, and these are the equations we will be working with. Now what we're going to do next is we shan't derive the equations from scratch in any great detail. Basically because of the limited time that we have in this course, and because we want to get down to solving problems, to analyzing problems, and to seeing how we can use mathematical methods to solve these equations and gain insight into practical concrete problems. So with that in mind, rather than deriving the equations from scratch, although that may be the best way to be familiar with them and to understand them, what we shall do here is to kind of sketch the derivation of the equations in such a way that motivates the different terms and that helps you attribute physical significance to these terms. So for example, when I say that this material derivative or convective derivative of velocity represents acceleration or inertia, what does that really mean? Why do I say that? Same for these viscous terms. How do we think of these viscous terms as stresses, as surface forces, in other words? It's not immediately obvious from here, and that's something that we shall understand in the next couple of lectures, or that I shall try to motivate by giving you a brief sketch of the derivation with some of the important points and concepts and ideas, but we won't really spend too much time in trying to do a rigorous derivation, as these are all available in standard text, and if you pursue the study of fluid mechanics or transport in graduate school, you shall certainly do these derivations in more detail. Okay, but before we start with studying these equations in more detail and looking at the derivation sketches of derivations, let us briefly return to consider what is the implication of having these equations for our study of our subject. So as I said, and as we saw now, the equations are well laid out, and these equations, especially the Navier-Stokes equations, have been known now since the 1820s. In fact, it's soon going to be 200 years of the Navier-Stokes. So then one might ask, what is left for us to work on? Is the subject of transport phenomena merely the application of these equations to practical problems? Well, the answer is in a sense yes, but no. What I mean by that is, yes, the equations are well known, with a caveat, of course, for complex fluids that we will come back to in a second. But by and large, certainly for simple fluids like water, honey, air, under normal conditions, room conditions, the Navier-Stokes equations apply very well. They have been well validated, and we have good reasons to be fully confident in them. So what then remains for us to do? Well, it turns out, if we think back to those equations that we just looked at, the substantial convective derivative ddt, which has the form of the local partial derivative with time plus v dot the gradient of the velocity or the concentration. So in the Navier-Stokes equations, this term, this inertial term, this v dot gradient of velocity is nonlinear, because there is velocity both when you look at the term v ddx of v, for example, plus vy ddy of v, and so on. These terms are nonlinear, and mathematically this means that the equations become very difficult to solve and allow for the problem to have multiple solutions under the same conditions. As a consequence, the solutions that we obtain from the Navier-Stokes are not only hard to come by but extremely difficult to understand. And so just because we have the Navier-Stokes equations, it doesn't mean that we understand the physics of the flow in all situations. More recently, yes, we can do direct numerical simulations of the Navier-Stokes and get predictions, but again, that is far from understanding the problem and why we see what we see. And this is really the focus of our course, is to learn methods and techniques that help us to gain such understanding. So this is why the subject of fluid mechanics and transport phenomena more largely remains vibrant, both in terms of application as well as importantly in terms of fundamental work. So to give you an example of what I mean, let's look at the famous Taylor-Couette flow and the sequence of instabilities it undergoes. So this is a movie from the National Committee of Fluid Mechanical Films, funded by the NSF of the United States, and it's available online at the link shown here. So let's take a quick look at this video. What's going to be done is there are two cylinders between which is placed a fluid containing aluminum particles, and the inner cylinder is going to be rotated while the outer one will be held fixed. And what you will see is when the rotation speed is small, the flow will be laminar. You won't see anything particularly interesting. But as the rotation speed increases, the fluid is going to do something remarkable.
Between two concentric cylinders. The inner cylinder turns, the outer cylinder is stationary.
So here we see the operator is inserting this cylinder, and now he's going to switch on a motor which is going to start rotating that inner cylinder. And so for slow rotation speeds, the fluid is, although you can't see it, is just moving in a laminar fashion. And now once he increases the speed, that laminar simple unidirectional flow goes unstable, and you form these toroidal vortices within which the fluid is following helical flow paths. And it's visualized by aluminum flakes which reflect differently depending on their orientation. And so where you see the dark bands is where fluid is going in, and so on. Here we see that the presence of some microbeads allows us to see this toroidal or helical motion within the fluid. So this flow state has really arisen because of an instability of the unidirectional state. So here we have an example where there are two solutions, a unidirectional one, a cellular one, and now we see yet another one where you have these cellular cells undergoing a sort of oscillation. So this is a third solution which has now come up because the earlier two solutions are unstable.
And still higher angular velocities.
And so you see the same Navier-Stokes equations under the same parameters is able to produce multiple solutions, some of which are unstable, some are stable. And now if you really increase the rotation speed, you get a fully turbulent state where it seems like those patterns are lost, but really if you look carefully, you can still see the vestiges of those Taylor-Couette cells. So the flow is fully turbulent in the sense if I put a probe, you'll see a randomly fluctuating velocity. It looks like there is no order, but yet at the macro scale there does seem to be some kind of pattern. And this is still an open question. We still do not understand how turbulent flow in general behaves, but also how you have these large scale patterns arising out of turbulence. So this is just one problem in which there's been decades of study and yet we do not fully understand it. And like this, there's a whole myriad of problems in fluid mechanics that still await understanding, even though they're all governed by the same Navier-Stokes equations. So as I said, the cause of this is the nonlinearity of the equations, the fact that the solutions, when they can be obtained typically numerically, are multiple in nature, they can have different stabilities, and often the solutions themselves are multi-scale and chaotic. By which I mean the smaller scales of motion compared to the scale of the system can be orders of magnitude apart, as it is for turbulent flows, for example, of clouds, where the smallest turbulent eddies in the clouds which impact droplet collisions are on the order of millimeters, whereas the size of the cloud itself and the atmospheric motions that govern its overall behavior is on the order of kilometers, if not larger. So you see, this is the inherent challenge of our subject and what keeps us going and keeps the subject interested. Okay, now to return to the asterisks that I placed beside the statement equations are well established. So as you may know, this is true only for simple fluids governed by Navier-Stokes, where the constitutive equation of a simple linearly viscous fluid holds, or the Newton's law holds. But for more complex media, like for example molten polymer materials or polymer solutions containing polymer molecules, suspensions of particles, or more exotically and of current recent interest, active fluids, for example suspensions of swimming bacteria and so on. In all these cases, although we can describe the material as a continuum, the constitutive equations relating the stresses in the material to the motion of the fluid are not known, and they are very hard to derive from statistical mechanics or from molecular models. And so these remain open areas of work, although in some simple cases we do have continuum equations, yet there are a vast variety of situations where we still await continuum formulations. In this context, more recently, it's becoming popular over the last couple of decades and ongoing to try and combine the continuum approach with molecular models, where you use the continuum equations to solve for the macroscopic flow. But at every point when we want to know information of the stress tensor, we appeal to some kind of molecular model to give us the stress by computation from the local flow conditions. So this sort of multi-scale computational approach is becoming increasingly popular and may in fact solve some of our problems in the future. But nevertheless, understanding the continuum principles even in such situations is important, because in any case, when you appeal to a microscale model, you have to find a way to relate the variables at the continuum level to the microscale, and then to go back from the microscale and average out and get the continuum information. And all of this requires not only an understanding of the molecular level description, but also the continuum viewpoint. Okay, so with that, I hope this lecture has given you a perspective about the continuum approximation and the equations that we're going to be working with. In particular, what I hope you have realized through this lecture is that there are some subtleties involved in the continuum approximation, in how it was arrived at by the founders, and have seen why we still use the continuum viewpoint quite fruitfully, that it is not merely a kind of coarse approximation because we just do not have computational power to do the molecular simulations, which is true. But I hope you have also seen that it is a powerful method in its own right, and that one can, by viewing it as a phenomenological model, it's really quite a valid way to describe macroscopic phenomena of materials, but which of course ultimately one should verify with experiment. So with that, we'll break off now, but come back in the next lecture to begin looking at a mathematical description of a continuum in motion, and from there sketch out the derivation of the governing equations and try and understand the physical meaning of the various terms involved. Thank you.